Now, 33rd question, assertion and reasoning type 1. In the analysis of statically determinate planar trusses by the method of joints, not more than two unknown bar forces can be determined. Correct? What is the reason? There are only two equations of equilibrium available for a coplanar concurrent forces system. Assertion is correct, reason is correct, and reason is correct explanation. I gave you in the first chapter in the note. Assertion and reasoning, why, how they ask you, it is like that. So 33rd question, option is A. Next 34. In the analysis of a truss by the method of joints, it should be ensured that the selected joint does not have more than two unknown member forces which are not collinear. Correct? The method of joints employs two basic equations for the free body diagram of each joint. Same question. Wording is only different. Assertion is correct, reason correct. Reason is the correct explanation for assertion. Next, 35. We have a system like this. Okay, there is a spring here. Okay, then here one more member vertical. Okay, there is a load W. This point is A, B, C, D, E. This is 1 meter, 1 meter, 1 meter. Now, this is a problem. The spring stiffness he has given K is 4 kilonewtons per meter. Members are inextensible, all that story is given. To keep CD horizontal, what is the value of W? Now you see 1 meter means this length is root 2 meters. BE length. Unstretched length, that means free length of spring. Free length of spring is 1 meter. Now BE length is now stretched length. Square root of 1 plus 1, root 2 meters. That means 1.414 meters. So elongation of the spring. Elongation of spring is 0.414 meters. Then what is the force in the spring? Force in spring BE. Let us call it as FBE. K delta, K into delta, 4 into 0.414, you will get 1.656. So force in the member FBE 1.656 kilonewton tension. So this much force is existing already. Force in the member BE is 1.656 kilonewton. For this force to be 1.656, how much W I have to apply? That's the question. Cut here. Look RHS. Cut BE by 1, then RHS of 1. Then unwanted forces are these two. These two are meeting at A. Take moments of all force about A equated to 0. Clockwise positive, anti-clockwise negative. So plus W into 2 minus 1.656 into 1, 1.656 sine 45 is the vertical component into 1 must be 0. So W must be 1.656 sine 45 by 2. Sine 45 means 1 by root 2. So 1.656 by 2 root 2. So you will get 1. 0.585. So 0.8585 into 2 minus f sine 45 into 1. So you will get now it will be in equilibrium. Okay. So 0.585 is the answer. Kilonewton. He is asking you in terms of Newton. So we can write it as 585 Newton. Next 36. Short by 2. This we have solved it. All members have same delta vertical displacement of r 2 mm. Upward you have taken. This is solved in class. Next 37. This is the question. These are very nearer. 1, 2, 3, 4. This is like this. Like this. Hinge roller. In the plane truss shown below, the number of members having zero forces. Now you see, we should not take them that they are equal. And we should also not take them that they are equal. General forces. Take general values. That means here it is a P, here it is a Q. Lengths are also not same. Under such circumstances, reactions are different. V1, this is V2. V1 is not equal to V2. Why? Not symmetrical loading. This case we have to take it. If they give you the values PP, then you can take them equal. Otherwise, no. Distances not given. So you have to take them as unequal distances. Under such circumstances, how many zero member forces? You see here, at a joint, two non-collinear members, no vertical load. So 0, 0. Whatever may be the values of PQ lengths are there, these two are 0. These two are 0. 1, 2, 3, 2 are in line, third must be 0. 1, 2, 3, 2 are in line, third must be 0. 1, 2, 3, 2 are in line, third must be 0. That's all we can tell. We cannot tell about the nature of these forces. So 4 plus 3, 7 members have 0 force. Panel shear we cannot take it because you do not know whether the value of V2 or this one. Then you sum of them whether it is 0 or not you cannot determine unless otherwise we know the magnitudes. So panel shear magnitude you don't know. If panel shear is 0 then we can say that this is 0 and this is 0. But panel shear we don't know. V2 minus Q whether 0 or not we don't know. So stand here, look right side, simply you can get V2 minus Q. Whether it is 0 or not, you don't know. So this is 0 or not, you don't know. So don't take it as 0. General cases means only 7 members have 0 force. Okay. Then 38. Now the ratio of vertical deflection to horizontal deflection at C in the given truss shown below. This is only numerical intensive paper question. Okay. Now you are applying load P. This is LAE. L to AE. This point let us say A, B, C. 45 degrees, 45 degrees. A he has given 500 mm square. That will substitute later. Young's modulus 2 into 10 to the power of 5. Okay. Delta vertical deflection of C by delta horizontal deflection of C. First we will calculate delta VC. Summation of P K L by AE is the formula. Now you see sigma x0, when you take it, both forces have summation must be 0, which means that these two forces must be equal. When I pull it down, it should be away. Away. Away means here also away. Away from the joint. Now symmetrically loaded. Now you see this F sin 45 plus F sin 45 must be equal to P. Forces when you want to P values. F sin 45 plus F sin 45. 2F sin 45 is equal to P. So F you will get P by 2 sin 45. So 1 by root 2. So you will get P by root 2. So this tensile force is P by root 2, P by root 2. Now what is the K values we can find? Directly we will take the step, this one. Member P, K, L, delta vertical deflection of C, summation of P, K, L by AE. Member AC, P is tension, P by root 2, K is 1 by root 2 naturally. Length is, length of the member he has given L itself. So PKL by AE. P by root 2, 1 by root 2 into L by AE. So you will get PL by 2AE, right? CB member same, PL by 2AE. So you will get delta VC is equal to PL by AE. So P, how much he has given? P kilonewton. Here member AC, PL by AE, here PL by P by root, force is same, P by root 2, 1 by root 2 into L by 2AE you have to write. So you will get this value as PL by 4AE. So delta vertical deflection of C, PL by 2AE plus PL by 4, 4 common, 2 plus 1, 3 PL by 4AE. Next, horizontal deflection. P values in this case are 0. Then K values only you have to find. This here will write. K values directly you have written. When P is there, P by root 2. 1 means 1 by root 2. Directly you can write. Next, delta horizontal deflection of C. Summation of P, K, L by AE. Then K values means unit load you have to apply like this. Unit load is here 1, 45 degrees. When I press it, this is under compression, but this is under tension, away from the joint. Okay. Now, if I take like this, how much is that? Both have to be equal. If I write sigma x is equal to 0, this is K1, let us say K2, you take it. K1 cos 45 minus K1 cos 45 minus K2 cos 45. They have to be equal. Otherwise, sigma y0 cannot be satisfied. Plus 1 is equal to 0. So K1 you will get 1 by 2 cos 45. That means you will get 1 by root 2. That means this is 1 by root 2. Now table member P, K, L, delta horizontal deflection at C, summation of PKL by AE. So member AC, member CB. AC member, if you take it, both of them are under tension. P value is plus P by root 2. This also plus P by root 2. K value. This is AC member, means this is C, this is A, this is B. So you will get K value how much for the member AC? 1 by root 2. Tension, so plus. Length is L. PKL by AE, that means PL by 2AE. Next CB member plus K value is, this is CB member compression, so minus 1 by root 2. Length is L. So you will get minus P into L by 2, 2 into 2, 2 into 2AE. Horizontal deflection also will exist because the structure is not symmetrical with respect to vertical line. Axial rigidity are different, so that's why it will move. So 2AE minus PL by 4AE. Here you have got tensile force, but whereas here horizontal displacement, it is compressive. If at all this is also AE say, then symmetry is maintained. So this minus this, it becomes 0. Now it will not become 0. So delta horizontal displacement at C is PL by 2AE minus PL by 4AE. So you will get PL by 4AE. Now delta VC by delta HC. This is 3PL by 4AE by PL by 4AE. So 3. 3 is the answer. So AE magnitudes, we don't have to use it because simply he is asking you to find the ratio. Now last question, 39. Since it should be over in 2 minutes time, I am assuming that just now you have studied the deflections in the trusses chapter. Then you have to go through this one. Then you will know whether you have finished in 2 minutes time or not. Otherwise, some sketchy draw, if I draw again, detailed explanation now not required at this stage. Now 39th question. A pin jointed truss shown below applied load is 100 kilonewton, 3 meters, 3000 mm square. This is also 3000 mm square. Brackets is in mm square. E value, some value is given. Okay. Pin jointed truss is there. length of inclined member is 3000, angle between so and so, cross sectional area is given, Young's modulus is given, vertical deflection of joint under a load of 100 kilonewton, P is 100, then this is the length is, this is 45 degrees, P, F sine 45 is P, so F is P by sine 45, that means P root 2, this is, that means 100 root 2 kilonewton away, then towards 100, this value you can take it as C B A. Okay, now you can directly take 3000 mm, this is 3 meters, 45 degrees means this has to be 3 meters only. Now you see PKL by AE, delta vertical deflection, summation of PKL by AE, member PKL AE value will substitute in the end, member AC, force P is 100 root 2 kilonewton, we will write in, this is kilonewton. When P is there 100 root 2, when 1 is there 100 root 2, 1 means simply root 2, length is 3 meters. Then delta VC, 100 root 2, 200 into 3, 6000. 200 into 3, 600 by AE. Then CB member, compression 100, so minus. So minus 1 you have to write. Length is 3 meters. So PKL 300 by AE. All areas are same, correct. So delta VC 900 by AE. 900, this is in kilonewton meter. That means this is actually 900 by AE is in meters. So you convert into mm. What is the area? 3000 mm square. So this you will write 10 to the power of minus 3 mm, you will get it. Young's modulus 2 into 10 to the power of 5 newtons per mm square. So Young's modulus also if you write 2 into 10 to the power of 5 newtons per mm square. Kilonewton means 2 into 10 to the power of 2, we have to write kilonewton per mm square. In meters 6 zeros will go up. So 2 into 10 to the power of 8 kilonewton per meter square. So we will write kilonewton per mm square only, will write it otherwise, because the other dimension is in mm, we have already kept. 200 we will write here directly. 200 kilonewton per mm square. So now kilonewton it will tally. Dimensions also will match. Meters you have converted into mm. Kilonewton we have kept it as it is. Kilonewton cancels out. So 1000, so 900 by 3 into 200, 600. So 9 by 6, 1.5 mm. So this is about the trusses. Now we'll see the matrix methods in structural analysis. Now let us see matrix methods of analysis. Now first question is, the rigid gable frame shown in figure is to be analyzed by stiffness method. So like this it is there. Okay, 20 kilonewton load. This is also 20. This let us say A, B, C, some D, E. 4 meters, 6 meters, 6 meters, 6 meters, 4 meters. 4I, 4I. Everything looks the same. But you see, I values are different for the columns, I to I. So, which means that the structure is not symmetrical. Mirror reflection is not there. If this is also I, then the frame will not sway for this loading. So, sway is 0 we can take. Now, but now we cannot take sway as 0. Both cases we will see, because this is frame sways. Towards left. So delta is present. Okay. Now let us calculate with that. Dk here it is 1. Here it will sway, it will rotate. Vertical deflection is 0 because it is axially inextensible. So here dk is 2. Here it will sway, but need not be the same amount. If it sways by 5 mm, it can sway by 2 mm. That's all, because both of them are independently can sway, because these two are not rigidly connected. If there is a horizontal member also, then if it sways by 2 mm, this will also sway by 2 mm. Member is not there. If it sways left side by 5 mm, it will sway by 2 mm. Can sway. So here dk is 2. What are they? Delta dx, theta d. Here delta bx, theta b. Both y directions are 0. Okay. Next here dk is 1. Here also dk is 1. Now here, since these two displacements are known, I can find xy displacements of this one. How much it can go vertically, how much it can move horizontally. Only unknown here is dk is 1, theta c. Once if I know xb, xd, I can find xc easily. Okay. So 1, 2, 2 plus 2, 4, 6, 7. If x displacements are known to us, y also we can find from the geometry of the structure. So x, y distances we can find, because theta is fixed. Because so small deformations, theta is same. So you will get 7 by 7. Delta xc and delta yc. Y deflection also can be there, but I can find delta yc can be found if delta bx, delta dx are known from trigonometric relations. Okay. So now total 7, dk is 7. 2 plus 1, 3, 6 plus 1, 7. So size of k, dk by dk, seven by 7. So first question B is the answer. Next, second one. Which one of the following statements is not correct? Flexibility square matrix, flexibility symmetric matrix, correct. All elements of flexibility matrix must be positive, that is wrong. Only diagonal elements are positive, other elements can be negative also. elements of flexibility matrix are displacements, correct? And can be computed only for the stable structures, correct? Stable structures only you can find. If it is unstable structure, when you apply unit load, large deflections will happen and you cannot find. Only thing is all elements of flexibility matrix must be positive is wrong. Only diagonal elements are positive. C. Only diagonal elements are positive. Other elements can be negative also. We have calculated many negative elements also, flexibility coefficients. Next, third one. 3-span continuous beam fixed at its ends. 1, 2, 3. 3-span continuous beam fixed at its ends and supported by 2 rigid supports in between. Order of reduced stiffness matrix for this beam. Theta B, theta C, 2 by 2 matrix. So dk is equal to 2. So 2 by 2. So third question is C. Fourth one. For the beam shown below, the stiffness coefficient K22. These are the coordinates. 1, 2, 3. K22 means you have to imagine that all elements are fixed. This is symbolic representation of fixing all the coordinates. K22 means force at coordinate 2 to produce unit displacement at 2. Like this. Now delta 2 is equal to 1. For this profile to happen, strength of MDM I told you K22. 12 EI delta by L cube. Now delta is 1. So 12 EI by L cube. So 12 EI by L cube, where is that B? A value will not come into picture at all. 12 EI by L cube. Next, fifth one. For a plain truss member, length is 2 meters. Okay. E value is given. Cross section is 200 mm square. Stiffness coefficient with respect to local axis. That means local axis means this member ABC. This is the coordinate 1. K11. Local axis you are taking. AE by L. What is the cross sectional area he has given? 200 mm square. Young's modulus is 200 GPa. So 200 into 10 cube newtons per mm square. AE by length. What is the length? 2 meters. That means 2000 mm. So 200, you will get 3 zeros gone. Then 1 2 is also gone. So 2 4 zeros. 4 zeros Newton. That means you will get 2 into 10 to the power of 4. Axial rigidity 200 mm square. Cross sectional area 200 GPa means 200 into 10 cube Newton per mm square. Then K11 AE by L. What is the length of the member? Length is 2 meters means 2000 mm. So you will get 4. Newtons per meter. Mm square, Newton per mm square per mm. Yes, AE by L means Newton per mm. Okay. Now 2000, these are gone. 3 zeros gone. 2 is also gone. 1, 2, 3, 4. So 2 into 10 to the power of 4 Newtons per, everything is in mm. So if you convert into meters, 1, 2, 3, 4 into 7, 2 into another 3 zeros you have to add, Newtons per meter. 2 into 10 to the power of 7 Newtons per meter. So B, fifth one is B is the option. Per mm is so much, per meter means into 10 cube. So 200, another two zeros into 10 cube Newton per meter. So 4 plus 3 is 7. Local axis means that. Now you see, as a note I'll give it for the earlier problem. This is 20 kilonewton, 4 meters I, 4 meters. This is also I, let us say 20 kilonewton. This is A, B, C, D, E. This is 4I, 4I. Now you see, structure is symmetrical, loading is symmetrical, so no sway. Symmetrical. So if it is symmetrical, slope must be 0. Whatever angle is there, same angle must be there. Then only when I fold it, this will sit on this one. So theta c is equal to 0. At axis of symmetry, slope must be 0. Now what are the decay? This decay here it is 1 rotation. Here decay is 1 rotation. 1 rotation can happen, but it cannot sway to the left or right. Here it cannot, if you see, once it doesn't go down, here slope is 0. Here at this point decay is 0 only. It cannot move vertically down because actually deformation, it's not swaying, not coming down. So it cannot come down, cannot move horizontal. So decay is 0 here. Here it can rotate. Decay is 1. Rotation such that here it can maintain same as it is. It can rotate, but it cannot rotate here. It cannot sway. It cannot move vertically down. Here decay is again 1. So 1, 2, 3, 4. So if symmetrical, dk is 4. So K is a 4 by 4 matrix. This you can use it only when, anyhow that option also was not there. So 4 by 4 matrix you will get if it is symmetrical. Okay, now let us see the sixth question. Sixth one. Stiffness matrix with respect to given coordinates. One, two. Now you see. Now coordinate 2. After fixing all the coordinates, then give unit displacement. Rotation you fix it. That means it cannot rotate. Without rotating, it should displace like this in the coordinate 1 direction. Coordinate 2 must be fixed. This length is L. This is hinge. As it is, you have to keep it roller. This is coordinate 1 here. Clockwise means here also it should be clockwise. Without rotating, I have to pull it down. Then how it will deflect? Like this. This is, for this one force we know, 12 EI by L cube. Because this delta is 1. Here also we know it is, far end is hinge means 3 EI by L cube. So K11, 12 plus 3, 15 EI by L cube. Okay. Now, because of this, what is the moment developed when it rotates like this? Here how much it is? Force at 2. Because of 1, 6 EI by L square. Here anti-clockwise. Here to make the slope 0, clockwise. Coordinate to given clockwise. This is anti-clockwise, so minus. Coordinate given clockwise. This is clockwise. This is plus 3EI by L square. So force at 2 because of 1. Both of them are clockwise, you have taken. Anti-clockwise, clockwise. Done. So you will get minus 3EI by L square. See, if it tallies 15EI by L cube minus 3I by L square. See, only one option is matching, one is sufficient. 15 and minus 3, you have got A. So directly put it as A. Other, you don't have to solve it and waste the time in the exam. Next, 7. This we solved in the class. 3A into 1 by A cube plus 1 by B cube. 7C. Then 8. Consider the following statements relating to structural analysis. Flexibility matrix and transpose are equal. Because of the symmetry, F and Ft are equal. When you transpose them, you will get the same. Correct? First statement is correct. Elements of the main diagonal stiffness matrix are always positive. Correct. For unstable structures, coefficients leading to diagonal matrix can be negative. For unstable structures, we don't define at all. Leading diagonal matrix can be negative. It is not negative, it is some infinity, that's all. So it cannot be negative, it will be infinity, because large deformations in the direction of force only will happen. So 3 is wrong. So 1 and 2 only are correct. 8B. Even for unstable structures also, diagonal coefficients, they are very large. Supposing that if you are applying relating to structural analysis means any matrix you take. You apply force downward, say. Displacement is also downward only. If it is stable structure, finite deformation. Unstable structure, large deformation but in the direction of the load only, but not opposite to that. So leading diagonals can never be negative. Okay. So third point is wrong. Next, 9. With respect to coordinates, what is the stiffness matrix? Coordinates are like this. This we have done, I think, 1. This is 3. This is 2. K11. First column. Symbolic representation of fixing. Coordinate 1. Let it elongate by 1. So K11. AE by L. This is K21, 0. This is K31, 0. So first column is AE by L 0 0. Oh, three options are same thing. That means second column you have to calculate. Second column. Symbolic representation of fixing. This is 1, 2. You give unit rotation like this. This theta is 1. K22. 4A by L. K1 because of 2, 0. K3 because of 2, 0. So second column is 0, 4A by L, 0. First column is AE by L, 0, 0. You see this one, anything matching? AE by L 0, 0, 4A by L. This is K120, K22, 4A by L. This is this one. So AE by L 0, 0, 0, 4A by L 2, 2, 3, 2. Now, when you have say K2 to 4EI by L, here moment how much will develop? Carry over moment 2EI by L. This is called COM. Clockwise, so anti-clockwise reaction is this way. This is 6EI by L divided by L. So you will get 6EI by L square. So K32 you will get 6EI by L square. Now see here 0, 4EI by L, 6EI by L square. This anything telling 0, 0, 0, 0, 4A by L, 6A by L square. Only now it's matching. Third column not required. So correct option is A. Ninth is A. Third we can also form, but how to get out quickly is the important thing. After solving the first column, we thought we should stop. But first column matching three options have the same first column. Then go for the second column. After second column, only one option matches. Say stop the work, don't go to the third column. Next one, 10th question. Stiffness matrix for the rigid frame with respect to coordinate axis generated. What is the value of K23? Only one value we have to find. This is coordinate 1, coordinate 2, coordinate 3. Now symbolic representation of fixing the coordinates. K23 means you should not permit it to sway, should not permit it to rotate. This is coordinate 1, coordinate 2, coordinate 3. Fix only the rotation. Coordinate 3 clockwise. Now the question is the K23. K23. Force at 2 due to unit displacement at 3. Give the unit displacement here in the direction of 3. Like this it will develop. So now this is theta is 1. What is this value is 4ei by L, we know. I have to apply 4ei by L. Because of that, force at 2. Because of the displacement, 2ei by L. What is this one? Carry over moment. So 2ei by L. So 10th question, D is the answer. Next, 11. Flexibility coefficient F12. This is the problem. This has given coordinate 1 for the reaction. Coordinate 2. Okay. He is asking F12. Displacement at 1. Due to unit force at 2 is nothing but K21 is also equal to F21. So this will take it now like this. Lengths are same. Apply unit force, curve, straight line. This is F2 because of 1. So this is how much WL cube by 3EI. 1 into L cube by 3EI plus slope is WL square by 2EI into L. Common factor 6, 2 plus 3, 5 by 6, 5 L cube by 6 EI. This you can write 10 L cube by 12 EI. We can write it as L cube by 1.2 EI. So D is the option. In the regular classwork, I stopped here, 5 L cube by 6 EI. That is nothing but 1 by 1.2 only. So flexibility matrix is given corresponding stiffness matrix. This we know how to manage. 12. Flexibility matrix is, he wants to call it as F say. 1 by EI, 36, 9, 9, 4. Then stiffness matrix is inverse. F inverse. That means 1 by EI means it will become EI 36 into 4 minus 9 into 9. So we have to make 4, 36 minus 9 minus 9. How many options match? 4, 36 minus 9 minus 9. So we don't have to calculate this result. This is matching with only one. 4 minus 9 minus 9, 36. So C is the option. That's all. Next, 13th question. For stable structures, okay, unstable structures we cannot derive. One of the important properties of flexibility and stiffness matrices is that the elements of the main diagonal always positive. Stiffness matrix must be positive. First one is correct. Must be negative. Second is wrong. Of a flexibility matrix must be positive. 3 is correct. 4 is wrong. So 1 and 3 are correct. So A, 13th question, diagonal elements must always be positive because of the Castigliano's theorem 1 and Castigliano's theorem 2. Next. Now we can write the reason here because of Castigliano's theorems 1 and 2. Why we have answered it as A? Next, 14. A member coordinate system shown in figure. Symmetric stiffness square matrix obtained by the member AB of length L, EI using slope deflection equation and rules of matrix multiplication as follows. See here, original member is here. This point is O. Joint O has deflected to A. Joint B has deflected to somewhere more. From here A has come down here, B has come down here. How much A has come down is delta A. How much B has come down is delta B. So two displacements are known to us. This rotation is clockwise. Like this it went. This is also clockwise. So something like that it has gone. If you drop a tangent, clockwise rotation is theta A. Moment is also MAB. Because of that, the reaction is SAB. Okay, this is delta B. Then tangent, when you write it, this is theta B. Then MBA. This is SBA. Correct sequence of, now the equation also is given. MAB, SAB, MBA, SBA. This is the matrix. He has given 2EI by L. Some symmetric matrix. This is theta A. Delta A by L. Theta B. Delta B by L. Whatever it is, first you write what is MAB. MAB means MFAB plus 2EI by L into 2 theta A plus theta B minus 3 into delta. With respect to left support, if right support sinks down, we have to take it as minus plus. So 3 into delta B minus delta A, 3 delta by L. Okay, this is our expression. So MAB. SAB means what? MFAB. First we will take this one. 2A by L common factor is given. So 2A by L into 2 theta A. 2 into theta A. Next, delta A by L. So delta A by L already given. So plus is there. Delta A by L means 3 should be there. 3 into delta A by L. Minus into minus plus. So 3 tallied. Next theta B. 1 should be there. Multiplication means like this. 1 into theta B. 1 into theta B. Next delta B by L. Minus. It should be minus. So minus 3. So 2, 3, 1, minus 3. Now you see 2A by L into 2 theta A plus 3 delta A by L minus theta B. So plus theta B minus 3 delta by L. So matrix multiplication is like that. So 2, 3, 1 minus 3. Is there option matching? First row 2, 3, 1 minus 3. 2, 3, 1 minus 3. C is the option. So from this we can get that some symmetric matrix. That symmetric matrix must be like that. Maybe loads were not there. SAB, etc. Everything can be automatically can be derived. So if you write this one, this will tell you how to write the slope deflection equation. We should have an idea. Then we can get that value. See here, 2a by L into 2 into theta a plus minus into minus plus 3 into delta a by L. Already delta a by L is there, so 3. This is over. Next, theta b, 1 into theta b. Then this minus 3 delta b by L, minus 3 into delta b by L. So everything matches. This is with respect to left support. Right support, if sinks down, your delta must be positive. That means minus q should be kept as it is. Delta b minus delta a is the net sinking. You have to take it. This is about 14. 15. Which of the following statements are correct? It is common practice to discount the influence of axial thrust on bending stiffness of members of frames. Correct. When compared to the bending stiffness, axial stiffness, you can neglect the influence because frames are mainly subjected to bending moment. Axial forces are very less. So first statement is correct. In a portal frame of single bay, columns have different thermal coefficients of expansion. Alpha is different. If the whole frame is subjected to same temperature, there will be a component of deformation in the vertical directions. There will be a component of deformation. Columns different thermal coefficients, one elongates, one contracts, different elongations will be there. Yes, there will be a component of deformation. One elongates more, one elongates less. So deformations will be there. If two different deformations are there, what that horizontal member will do? Try to keep it horizontal. So it deforms. One member it will push it, one member it will be pulled. In an attempt to keep it in the same level, one will be pulled, one will be pressed. So deformations will develop in the vertical direction. Correct. Flexibility method of analysis cannot be used to solve any kind of indeterminate structural problem. Which of the following statements are correct? Common to discount, 1 is correct, 2 is correct, 3 cannot be, 3 is wrong. You can solve any type of indeterminate structural problem because you remove the redundants, make it statically determinate and solve the problem. We can solve it. Cannot be solved means it can be solved. So 3 is wrong. So 1 and 2 only are correct. So 15C. If E says flexibility method of analysis can be used to solve any kind of indeterminate problem, it will be correct. Cannot be used means wrong. So only 1 and 2 are correct. Fundamental difference between flexibility stiffness methods of analysis of statically indeterminate structure. Flexibility method chooses the redundant reactions, correct, or internal forces, while stiffness method considers the nodal displacements as basic unknowns, correct. One is force method, one is displacement method. The number of simultaneous equations to be solved in the flexibility method will be very much smaller than the number of equations involved in the stiffness method. That we cannot tell because it depends on ds and dk, simultaneous equations to be solved. Very much smaller you cannot tell. If ds is more than dk say, then flexibility matrix number of simultaneous equations will be more. So B is wrong. In flexibility matrix, equations of equilibrium will inevitably be unsymmetric and less sparsely populated, while the stiffness matrix is always symmetric and sparsely populated. Equations of equilibrium will be unsymmetric. C is also Wrong. It is not unsymmetric, it is symmetric there also. Flexibility method is suitable to structures with smaller degree of statical indeterminacy than kinematic indeterminacy. Flexibility matrix is suitable to structures with smaller ds than dk. So D is correct. Flexibility method chooses the redundant reactions while stiffness method considers nodal displacements as basic unknowns. 1 and D are correct. Now the fundamental difference. Okay, fundamental difference when he is asking, not the characteristic. Flexibility is used for when ds is less, you can use it, but that is not the basic difference. Flexibility method chooses the redundant reactions or internal forces, and stiffness method considers as the nodal displacements as the basic unknowns. This is the fundamental difference between the stiffness matrix and flexibility matrix. Not whether ds suitable, whether ds is less or dk is less. That is not the fundamental difference. So correct option is 16A. D is correct, but it is not the fundamental difference. How you use, where we use for suitability is not the fundamental difference. Okay. Next, 17. This I solved in the class 6 delta. Next, 18. Now you see, it's like this. There is a roller support. Coordinates are 1, 2, 2i, L, I, L. For the structure shown in figure with the loading symbolized 1 and 2, what is the stiffness matrix? K11. Fix it first. This is 1, this is 2. There is a roller. Fix it. Here coordinate 1, 2. Okay. Now K11. If I stiff move it like this, this is delta 1 is equal to 1. We know K11, 12E, I means 2I. 12EI by L cube. That means K11 is 24EI by L cube. This one K21. He is asking what? Oh, K21. 6EI. I means 2I. 6EI delta by L square. So this is K11, K21, 12EI by L square. Next, 1. Here if you push it by 1, delta 1 is equal to 1 say, without push. This simply rolls out here. Here K11 in this case is 0. Okay. Force required to produce unit displacement is fix it, push it. Because there is a roller, easily it will move. Rigid body translation. If you fix it here, say, then AE by L we could have written. Roller means simply rolls off. So this is the first column. Then second column. Here is I will write. Fix it. This is coordinate 1, coordinate 2. Here same. This is roller. We should not touch the roller. Coordinate 1, coordinate 2. Now apply unit rotation here. If you apply unit rotation, the deflection profile is like this. K22. 4EI means 2I. 4EI by L. Because of that here 2EI by L. Then both of them are clockwise. Then here anti-clockwise. Clockwise. Here you see the moment that will develop is K21. Moment is like this. K21. So minus should be there. Minus 12EI by L square. Here also you see both of them are clockwise, and here 4 plus 6 plus 8, 8 plus 4, 12. So this is force at 1 because of the displacement, 12 EI by L square. Acting minus opposite direction, so minus. Here nothing is required because it simply moves. When I apply clockwise moment, the deflected shape is like this. It simply rotates this way. We want to give theta 1. Here also theta is 1. For this profile we know K22. 3EI means I only. 3EI by L. So now K12 is minus 12EI by L square. K22. 4 into 2, 8. 8EI by L plus 3EI by L. 11EI by L. So your stiffness matrix K becomes, first column is this one, 24 EI by L cube minus 12 EI by L square. This is minus 12 EI by L square, 11 EI by L, like this. So that is the stiffness matrix. This I think I remove. Oh, options were given already. Then 24 EI by L cube minus was missing. Here they didn't give any minus symbol. They have to give us 24, 12, 12, 11. EI by L also was there. 11 EI by L, 24 EI by L square, 12 EI by L. The one of it. Now 18th question, A is the option, you have to take it, but where he didn't give you that minus sign. But doesn't matter, there may be that clockwise, anti-clockwise couple may be there. But as we see, when I push it to the right side, to make the slope 0, moment will act in the anti-clockwise direction, but coordinate 2 is clockwise. So you have no choice, at least other than minus symbol, everything is matching. So 18th question, A you will answer. So take 12 as minus 12. Okay. Now let us see the 19th question. We solved in the class. We have taken 24 EI delta by L cube and 2 minus 1 minus 1 2. 19th solved in class. Matrix methods. Okay. Next 20th again solved in class. K11 AE by L root 2. K11 we have solved. 21 solved in class. 173 means C is the option we have taken. These things you can check it out. 22nd. While the other elements of the flexibility matrix may be positive or negative, the elements lying on the leading diagonal are always positive. Correct. Reason: the displacement at any coordinate due to a unit force at that coordinate is always in the direction of unit force. Assertion is correct, reason is correct, and reason is the correct explanation for assertion. So 22 is A. 23. Force method of analysis is not convenient for computer programming. I gave you the reason. Reason: bandwidth of flexibility matrix is much larger compared to that of stiffness matrix. Reason is also correct, but that is not the correct explanation for the not suitability of computer programming, because you can take different choices depending on the choice of redundance is not unique. Whatever redundance you take it, flexibility matrix different, the compatibility conditions are different. But because of that, bandwidth means the positive element, you get a band in a stiffness matrix or flexibility matrix, bandwidth will be generally large. That means positive elements will be more in the force method. So assertion is correct, reason is correct, but reason is not the correct explanation. Then reason is not correct explanation means B. 23B. What is the correct explanation or correct reason? Choice of redundants is not unique. That's why not suitable for computer programming. That's what I gave you. Next 24. This also given structure 1, structure 2. In the structure 1, choice 1 he has given only forces as the redundant reactions as the coordinates. Choice 2 they have given moments as the redundants. Next, figure for the continuous beam shown in the above figure, while applying force method, two choices of releases are available as shown in figure 2 and 3. Choice 1 is preferable since it will result in conditioned matrix. One is assertion is wrong first of all. One is not preferable. Reason: well conditioned matrix has leading diagonal terms dominant, which results in accurate solution. That is correct. Reason is correct, but assertion is wrong. A is false, R is true. One preferable. Reactions are not preferable. Results in conditioned matrix. So one is false, reason is correct. A is false, R is true means D. So 24D. Choice 2 is preferable. As I told you, choice 2 is preferable because you will get a well conditioned matrix which will give you accurate solution. Okay. The determinant of stiffness for the matrix shown in figure, determinants simply are that we are not interested. Stiffness matrix is also given, area of cross section is given, value of alpha. That stiffness matrix we can develop a 2 by 2 stiffness matrix, that is of simple calculations. We have solved many such problems. in the class. So this is not required. The value of alpha. A 2 by 2 matrix he is asking you to form. Then the value of alpha. Otherwise, we'll take that 26. Let us see the 25th also. Some problem they have given. Coordinate 1, coordinate 2. This is 2i, I, 2i, 4, 4, 8 meters. Now let us see K11, first column. Symbolic representation of fixing the coordinate. Clockwise 1, clockwise 1, clockwise 2, 4, I, 4, 2i. Okay, apply unit displacement like this. This is K11. 4ei means 2i by 4. And here also K11. 4ei by 4. So if I give unit rotation, it will displace like this. Theta is equal to 1. Because of this carryover moment, K21, 2ei by L. Nothing is carried over to that. So first column K11, 8ei by 4 means 2ei. K21, 2ei by 4. That means ei by 2. So 2.5. Then K22. This is the first column. Then second column we'll write here. Second column means I have to show only second and third. Coordinate 1, coordinate 2. Coordinate 2, that's all. Nothing here. This is 8 meters, 2i. Okay, this is 4 meters, I. Only second, third spans we are writing. This is K22. Like this. 4ei by 4. Carryover moment K1 because of 2. 2ei by 4. This is ei. Here K22. If you apply unit rotation, it will go like this. Theta is 1. So K22 will get 4ei means 2i by L. So you will get ei. So your flexibility stiffness matrix K is this one. First column 2. Ei common factor will take it. 1.5. Here 0.51. He is asking determinant. So 1 into 1 minus 0.25. So 0.75. 1 into 1 minus 0.5 into 0.5. He didn't ask determinant. Determinant of stiffness matrix for the beam shown below with respect to coordinate 2 is EI whole square. Okay, into EI square. EI into this, EI into EI square. EI whole square into, okay, 0.75 E square I square. So 0.75 is the answer. Next, 26th. We wanted stiffness matrix for the pin jointed frame. This is shown as 10 ton. Some value of the force 10 ton here. This is coordinate 1, coordinate 2. This is 4 meters, 3 meters. Okay. That EI value we can substitute later. 100 and 200 mm square. This point is say A, B, C. Okay. This is say theta. Tan theta is 3 by 4. That means 36.87 degrees. Now theta AB you have to take it as 180 degrees. Theta AC 180 plus 36, 216.87 degrees. So a 2 by 2 matrix means you have to write like this: member, then AE by L. Axial rigidity is different, 100 centimeter square, 200 centimeter square. So we can write AE by L value, then theta cos theta sin theta, then AE by L cos square theta, AE by L sin square theta, then AE by L cos theta sin theta. This much you have to take. Remember AB. AB AE by L. For member AB, AE by L. 100 centimeter square. Young's modulus 2000 tons per centimeter square. AE by L. Length we can take now 400 centimeters. So you will get 2000 by 4 means 500. So this you will get 500. Theta 180 degrees. Next, AC member. AC member 200 centimeter square. E means 2000 tons per centimeter square. By length is AC member 5000 centimeter, 500 centimeters. Okay. So you will get 500 means 4 into 2 8, 800. Theta 216.87. Now you can fill this one. This is K11. Add them. K11 summation of AE by L cos square theta. This is K22. AE by L sine square theta. This is K12 summation of AE by L sine theta cos theta. He is asking already 384 he has given. K11 means this only you have to calculate. So sigma AE by L cos square theta. How much you'll get? We will finish off that. Cos 180 is minus 1. So you will get minus 500 itself. Okay. Then next, you will get 640 cos square theta plus 640 1140. Yeah. Yes, tell me, madam. From Rishabh. Hmm? Hmm. You will get AE by L 1140. Cos square theta, even if you get minus means minus into minus plus. Okay. 6, 0.8 into 0.8, 0.64, 0.64 into 8, 0.64. This you will get 512. This one 500 itself. So you will get 1012. This only calculation AE by L sine square theta. So this value will get around sine 180. AE by L sine square theta, this is 0. Then minus 36.36 into 800. You will get 288. So this they have already given. K11 is 1012, 288. So that we will write directly. Only alpha is asking this one. So alpha is equal to 1012. So like that a 2 by 2 matrix K12, K21, you can directly fill the other quantities in the table. So this is about the matrix methods in structural analysis. Okay. Okay. Now we'll see the 7th chapter. Cables and suspension bridges. Now, first question. Match list 1 and list 2. Select the correct answer. The shape of a cable The shape of a cable suspended between two supports is defined by shape of a cable suspended by two supports is defined by a catenary. That means A is 1. A freely suspended cable, it sags due to its own self weight. If it sags due to its own self weight, then it takes the shape of a catenary. Next, B. Cable uniformly loaded along the horizontal span takes the shape of the parabola. B is parabola B3. The cable along its length, uniformly loaded along its length, assumes the shape of uniformly loaded means again a parabola. Uniformly loaded along the horizontal span takes the shape of parabola. This is also parabola. Along the horizontal length, uniformly loaded along its length assumes the shape of A1, B3, C, C4. If A1 and B3 are correct, A is catenary, B is 3, then all other things must be correct. A1, B3, C4, D2. Directly you put it, C4, D2. Then what is C is, the cable uniformly loaded along its length assumes the shape of the 4, shape of applied loads. Next, let us see, fourth one. The girder in a suspension bridge transmits to its supports. Girder in a suspension bridge transmits to its supports a little load, that we can take it because D4. D4 is correct. Actually, it is D2, little load. Because in a suspension bridge, if it is subjected to the girder, main girder, 2-hinged girder or 3-hinged girder, when you take it, I have told you about the hangers. If at all the 2-hinged stiffened girder or 3-hinged stiffened girder is completely subjected to UDL throughout the length, then support reactions are zero. Entire load is taken by the hangers and hangers will transfer load to the main cable. If at all UDL is not there, some other load is there, say, then majority of the load is taken by the hanger bars, very little load only will be taken by the supports. So this is correct. But C, cable uniformly loaded along its length assumes the shape of 4 he has given. C is D2C4. Then we have no choice. Cable uniformly loaded along its length, we must assume that uniformly loaded by the point loads, let us say. Then shape of the applied loads means no meaning at all there actually. But this we have to excuse. This is C4, you remove it. A1, B3, D2 is clear. Then C4 we have to leave it off because it has no meaning. Loaded along its length assumes the shape of applied loads. What he wanted actually to tell is it will take the shape of the bending moment diagram when when it is subjected to, or when, if you take an imaginary simply supported beam subjected to same loads, then the bending moment diagram, whatever bending moment diagram it takes, that shape the cable will take. Instead of writing that so much story, simply they have written simply applied loads. But instead of applied loads, you should write it will take the shape of the bending moment diagram of an imaginary simply supported beam subjected to applied loads. That much story should be there. Okay, since that much story he didn't give it, so we have no choice. So C4. So first question 1, 3, 4, 2 means B. Next, second question. Consider the following statements. Even though a three-hinged parabolic arch is subjected to vertical loads, it generates horizontal reactions and axial forces. Correct? Because we have seen horizontal thrust and also normal thrust. A cable uniformly loaded along the horizontal span assumes the shape of a parabola. Correct? Whereas if it is loaded along its length, along its curved length, it takes the shape of catenary. 2 is also correct. Cables uniformly loaded along horizontal span are by far the types most commonly used structures in practice is also correct because horizontal loads only will be there. So which of these statements are correct? 1, 2, 3. Third question. So second question, D is the answer. Because generally horizontal UDL will be there, curved length, no load can be applied. Which of the following statements are correct? For statically determinate structures, magnitudes for maximum effects due to a series of concentrated loads can be established with the aid of influence lines. That is correct. Maximum effect can be obtained by influence line diagrams. Cables in suspension bridges will not take the parabolic shape if uniformly loaded along the horizontal span. So second statement is wrong. Will not take the parabolic shape if loaded along the horizontal span. They will take the parabolic shape only when loaded along the horizontal span. So second statement is wrong. Now third one, a three-hinged arch structure, the normal force, shear force, bending moment at any section are not influenced by the horizontal reaction at the support. No, it is influenced by the horizontal support. So if you take the normal thrust at any section, HA into cos alpha, VA into sin alpha, like that you have taken. Normal thrust, you have the component radial shear, also horizontal thrust will come. Bending moment also you will get H into Y component. So horizontal reaction influences normal thrust, radial shear, bending moment in a three-hinged arch. So third statement is also wrong. Which of the statements are correct means one only. One only means B. 2 and 3 statements are wrong. 2 and 3 statements are wrong. They are influenced. Next, fourth one. A suspension bridge with a two-hinged stiffened girder is statically indeterminate to 1 degree. I have calculated ds is r minus s. I have given you this one. 4 minus 3 is equal to 1. Next, we solved in the class. Fifth point. A cable of negligible weight is suspended between 2 points spaced 300 meters apart. Between 300 meters apart horizontally, with the right support being 12 meters higher than the left support. Something like this. This horizontal span is, it may be going something like this, say. Now, this distance is 12 meters. 12 meters. Whether it is higher or not, we don't have to worry. 300 meters horizontal distance. Okay. With right support being 12 meters higher than the left support. 4 vertical loads of magnitude 4, 2, 4, 1200 are applied at A, B, C and D. Like this. First one is 400 kilonewton. This is 200 kilonewton, 400 kilonewton and 1200 kilonewton are applied at points A, B, C, D. A, B, C, D, let us say. This point you take now E, F. 60 meters respectively from left support. This is 60 meters. Then 120 meters means this is also 60 meters. Also 60 meters. plus 60. This is also 60 meters. 240 plus 60, 300 meters. All are equally loaded. The largest sag of the cable will be at. Largest sag will happen where the bending moment is maximum in an imaginary simply supported beam subjected to same loads. So you take a 300 meters span. This point is E, F. Total length is 300 meters. 4 loads are there. 1, 2, 3, 4. 61. Okay. Here there is one load, 400. This is 200. This is again 400. This is 1200. This is A, B, C, D. All are 60 meters. 60, 60, 60, 60. So first you calculate, as we have told you, Vf. So when you find the reaction at Vf, take moments of all force about E equated to 0 minus Vf into 300 plus 400 into 60, 400 into 60 plus 200 into 2 into 60 plus 400 into 3 into 60 plus 1200 into 4 into 60 must be equal to 0. Next, what is Vf? So Vf I can get 400 into 60, 60 common if I take it, 400 plus 400, 200 into 2, 400 plus 4 into 3, 1200. Then 12 into 4, 48. 4800 by 300. Okay. So 60, this will become 5. Now 4 plus 4, 8. 8 plus 12. 2 plus 48. 6800 by 5. So 5 ones, 3, 18. 5 3 is 15, 30, 60, 13, 60. So 1360 kilonewton. You don't require any calculator for that. This is 1360 kilonewton. Okay. Maximum bending moment occurs where shear force changes its sign. So where shear force changes its sign means we should not calculate maximum bending moment, then under that wherever maximum bending moment is, maximum sag is there. But where maximum bending moment happens is wherever the shear force changes its sign. Maximum bending moment we should not calculate because calculators are not given. So accordingly you see 1360. See here, section right side upward 1360, negative shear force. Come like this, up to here same. Cross 1200. 1200 plus 1360 minus. So still 160 is there. Move like this, cross. Now you see, now it will change its sign because this is 1600, 1360. So shear force changes its sign at C. So where shear force changes its sign? Shear force changes its sign at C. So max BM occurs at C. So max sag, maximum sag occurs at C under 400 kilonewton load. So 400 kilonewton load means fifth question 400 at C. Fifth question C is the answer. You see, nowhere we used the calculator. Here also we should not use this as 120, then 180, then 240 as you say. Then again you have to cancel the terms and waste our time. So right, in terms of 2 into 60, 3 into 60 only, cutting becomes simpler. You don't have to again use the calculator. These are the techniques of how we should get out of the problems. When calculators are not there, as far as possible, we should tend to cancel the terms. Okay, next. This is the fifth one, you understood. Then sixth question. Consider the following statements regarding suspension cables. Horizontal component of the cable tension in a suspension bridge is constant at every point along the length of the cable. I told you when the cable, when you have taken, x component is Tx, T minimum is equal to horizontal thrust we have given. At any point when you take it, x component is T minimum. Then that is nothing but the topmost point, horizontal thrust. When you draw the free body diagram, I have given you that horizontal component of the tension in the cable is always equal to horizontal thrust. So is constant at every point, is constant whose magnitude is horizontal thrust. So first statement is correct. Stiffening girders in a suspension bridge carry only live load. That is also correct. Dead load it will not carry because stiffening girder will not carry dead load. Because I told you when a suspension bridge is there, if you have uniformly distributed dead load, let us say, then entire downward dead load is there, upward cables, the suspension hangers are there. So hangers are like upward UDL, the dead load is like a downward UDL, they balance each other. I gave you one example of a wooden log floating on water. Wooden log sulfate acts downwards, water reaction upward. Strength of material sir told you that bending moment is 0 everywhere, shear force is 0 everywhere. So is the case here. Beam will not be loaded at all. But when live load is there, it's like a point load or some other part of the beam is loaded, say. Then hangers will take some load, majority of the load. That means hanger bars, little amount of reaction will be there at the supports. So this statement is also correct. Suspension grade stiffening girders in a suspension bridge carry only live load, not the dead load. So which of the above statements are correct? Both 1 and 2. Okay. Sixth question C. Then 7. An assembly made of arm, rigid arm is there. This is a rigid arm, you can take it. There is a rope at the same level he has given. This is a hinge. Here there is a rope. Okay. Rope or cable, whatever way you want to take it. It can only take tension. Rigid arm. This length is L. L. This horizontal length is also L. Okay. Height is also L, means angle of inclination is 45 degrees. You applied a load P here. Okay. An assembly made of rigid arm ABC, hinged at A, supported by elastic rope C and D, fine, and C as shown in figure. The members may be assumed to be weightless and the lengths of respective members are also shown. Under the action of concentrated load P at C as shown, P as shown, this is C, we can take it. This point say A, this is say B, C, D. Okay. At C as shown, the magnitude of tension developed in the rope. This is engineering mechanics problem actually. Magnitude of tension developed. Cut here. Then it will fall down. Now it is not falling down, means what the rope will do on this one? It will exert only one tension. Okay. At an angle of cos 45. Take the moments of all forces about A. Yes, sigma MA is equal to 0. Clockwise positive, anti-clockwise negative. Plus P into L minus T sine 45 into L is equal to 0. So T is equal to PL by L sine 45. L can, sine 45 means 1 by root 2. That means P root 2 kilonewton. So seventh question, P root 2. Root 2 P. So seventh is D is the option. Now, when we started cables and suspension bridges, we assume that you have opened that cables chapter, then study completely, then try to understand. Such problems we have solved in the class. Then first you should solve them, then check whether you have solved it correctly or not. Simply solution also you see correct, 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 but we didn't learn anything type feeling will come. This is the choice, this is the way for you to think on your own, to check whether you have understood what I taught or not. This also you take it, so then in the exam you have to test whether you have understood it or not. Now let us see the eighth question. Stop. Now you see we have a 3-hinged stiffened girder suspension bridge. It is has a span of total span is 120 meters and subjected to 2-point loads 240 and 300 at a distance of 25 and 80 meters. If the suspenders are transmitting an equivalent UDL of load Q naught kilonewton per unit length, value of Q naught is. How we have to calculate is, we have a cable and cable it is subjected to uniformly distributed UDL. Then because of that uniformly distributed UDL, Q0 he wants to take it. See here, if you take this free body diagram of the cable alone, this is the cable, let us say. It is subjected to uniformly distributed load coming from the hangers. Here hangers are there. Okay. This load you call it as Q0 kilonewtons per meter. This is what he is asking. When load is there, this horizontal thrust, we know what its value is. HA, this is B, let us say. HB is equivalent load Q0 WL square by 8H. It is like a simply supported beam subjected to UDA. This value we have already calculated. HA is also Q naught WL square by 8H. How will you calculate bending moment at this point? Let us say C. Bending moment at C is equal to 0. That same point we are taking. Then VA into L by 2 minus HA into H minus WQ into L by 2 into L by 4 is equal to 0. Then from this we know how to calculate horizontal thrust, WL square by 8H. Or I have given you WL square by 8H, but he wants to call it as Q naught, but we have written it as WL square by 8H, where Q naught is equal to W. Now you want to find that same equivalent UDL must be there on the beam. This is the actual simplest. We will assume this as an imaginary simply supported beam. Okay, subjected to same loads 240 kilonewton and here 300 kilonewton. Okay, this distance is 25 meters, 55 meters and 40 meters. Okay, this point let us say is already ABC we have taken. This you take D, E. Some value. Total span is 120 meters. This length is 120 meters. Now, due to these two applied loads, what's the bend moment at C you find? That bend moment at C must be equal to bend moment at C here, because this, due to these loads, whatever bend moment you are getting, due to equivalent UDL, same bend moment you should get. Then that bend moment is equal to HA into H. Okay, like that. That's how you will calculate the value of the horizontal thrust. For this case, bend moment at C, if you want to find, what we have to do, this is VD, let us say VE. Take moments of all force about D is equal to 0. So this is the calculation. Bend moment at on imaginary simply supported beam. Bending moment at C. This is the aim. Okay, same bending moment should develop here. And that bending moment HA into this whatever this distance is there, that should balance. This value is 12 meters. Okay. Now let us see. This is Q naught we have taken. These two also should produce same thing. Now VE minus VE into 120 plus 240 into 25 plus 300 into 55 plus 25, 80 is equal to 0. So from this VE you will get VE, you will get 250 kilonewton. VE is 250. Then bend moment at C, VE into 60 minus 300 into 20. This is 250 into 60. So you will get bending moment at center. Okay, this value works out to be 9,000. 9,000 kilonewton meter. This is 6,000. 250 into 6 means 15. 15 minus 6, 9,000. So bending moment at C is so much. Now bending moment at C we calculated 9,000 kilonewton meter. This is equivalent to this one, HA into H. This is on the cable. Bending moment at C is equal to 0. So minus HA into H plus equivalent UDL. It is UDL subjected to this means WL square by 8 Q0 into L by 2 into L by 4 must be 0. So what is HA? Is nothing but Q0 into L square by 8H. Okay. Now this you can get it as like this from the equation. Horizontal thrust we can get it. This is MC, WL square by 8. WL square by 8 means it is like MC, bending moment at C, by H. So HA, horizontal thrust at A is equal to MC, bending moment at C is 9,000 kilonewton meter by H is 12 meters. So horizontal thrust you will get 750 kilonewton. Now this is also equal to Q0 into L square by 8H. So Q0 you will get 750 kilonewton into 8 into H is 12 meters by L square. L square length is 120 square. So this you will get this is equivalent load Q0. Okay, this is 750 we have taken. Okay, 750 into 8 into 12 by 120 square. So you will get 5 kilonewton per meter like this. So this is the solution. We will take this beam as a 3-hinged stiffened girder as an imaginary simply supported beam subjected to same loads. Find the bend moment at C. Whatever bend moment at C you are getting in the UDL, when you are taking that UDL must give same bend moment at C. Okay, that is called equivalent UDL. Whatever these two loads are giving the effect at center, same effect it should give this load also. This is separate, this is separate. Due to this, what is bend moment at C? Then this will produce same thing here. Bend moment at C should be same. That's why it is called point loads are replaced by equivalent UDL, which will produce same bend moment at center. Now Q into L square by 8 is a bend moment simply supported beam subjected to UDL. So WL square by 8, that formula we know, minus HA into H must be equal to 0. So bend moment we know already, that means H we can find. So once HA is known, Q only we don't know here in this case. So since H we know, Q0 we can find. Next. Now let us see the 9th question. Okay. A pole AC, we have a pole here. It is hinged here. This is L by 2. Then at L by 4, that means somewhere here, we have attached cables. These are cables or ropes we can take. Rope. This is also rope. Rope is like a cable, can only take tension. When subjected to compression, they get slack. It will be 0. This point, let us say, somewhere here B. So from here to here it is L by 4. We have connected at center. Cable is connected at center. Okay. L by 2. Somewhere here it is there B. A, this A, B, C. This is the center point. L by 2. From here to here it is L by 4. Here to here it is L by 4. You are applying a force W. From here to here this length is L by 2. L by 2. That means what? Angle of inclination is L by 2. L by 2 means 45 degrees. Here also rope angle of inclination is 45 degrees. Okay. This before the application of the load at top, tension in the rope is just greater than 0 means just taut. TIUT means just tension existing, that's all. Initial tensions are not there. If a point load is applied at A, then bending moment at B will be, here we want to find bending moment. Now let us see how to find the bending moment at B. See, when you are drawing the free body diagram, see, this is the bar, this is the rope. When I push it like this, assume that it deflects like this. This will be subjected to compression. That means force in this rope is 0. This will be pulled when I am pushing it like this. Let us call first this as tension T after cutting them. Okay. So one unknown is there. We want to find bend moment at B. First take moments of all force about C equated to 0. This is the free body diagram. Okay. So bend moment at this, the free body diagram is cut the rope, throw it out because it's at 0 force. Cut the rope, throw this out. What is doing this is one tension T. That's all. That feel must be there when ropes are attached, how they behave. So bend moment at C is equal to 0 plus W into L minus, this is 45 degrees. T cos 45 is acting like this. This is T cos 45. And vertical is T sin 45. But T sin 45 will give 0 moment about C minus T cos 45 into L by 2 must be 0. So T is equal to W by L by 2, it is there, goes here, 2 W by cos 45. Cos 45 means 1 by root 2. So 2 root 2 W. So LL cancels out. 2 goes this side, 2W by cos 45. Done. So this is tension. Rope cannot take compression. Okay. Now tension is known. Bend moment at B. Stand at B and look up. So this is plus W into 3L by 4 minus T cos 45 into L by 4. That's all. So you will get, what is T here? 2 root 2 W. This is 2 root 2 W. So 3W L by 4 minus 2 root 2 cos 40 means 1 by root 2. Cancels out, minus 2WL by 4. So you will get WL by 4. So bend moment at B is WL by 4. So the answer is WL by 4. Ninth question, C is the option. That free body diagram only is important. 10th one. Maximum possible span for a cable supported at the ends at the same level, assuming it to be in a parabolic profile, allowing a central dip of 1 by 10th of span, that means L by 10, with permissible stress, that means the 150 newtons per mm square is the permissible stress. Then specific weight is also given, 78,000 newtons per meter cube, or in other words 78 kilonewton per meter cube will be nearly. This type of questions where it is calculation intensive, we should not attempt in the exam, because where calculators are not permitted, we cannot solve it in 2 minutes time. Okay, because results are, you see, 1330, 1388, so close results are there. So we must withdraw and solve the some other problems. But if you have to solve it, then it should be done like this. I'll give you the solution. Now, see here, this is the problem. We have a cable, span we don't know. We have to find the span. This is like this, subjected to uniformly distributed UDL. This is span L. This dip, this value has given H is equal to L by 10. So that is the dip of the cable. Then length of the cable. This is the actual length, curved length. Also we can take it. This is subjected to at the ends at the same level, allowing the stress. Permissible stress is given. Weight of steel is given. That means curved length we have to find. So weight of steel is given. That's why you have to take the like this. Dip of cable L by 10 given. We say okay. Then length of cable, because specific weight of steel is given. So we have to calculate length of the curved length of the cable is actual span plus 8 by 3 into h square by L. I didn't derive this formula. This parabolic equation, if you take it, that curve length you will get. So we can write it as L into 1 plus 8 by 3 into h by L is 1 by 10 square. 1 by 10 square means 1 by 100. Okay. So you will get this value as 308. 308 L by 300. Now, area of the cable, cross-sectional area of cable. Let us say capital A. We don't, because specific weight is given. Then weight of cable, specific weight into volume. That means gamma AL. This has given 78 kilonewton. That means 78,000 Newton into area into length. Length is 308 L by 300. So you will get this weight is 0.08008 A into L. Then vertical reaction. This point, let us say A, B. This is the cable weight curved length has given. So VA is equal to, vertical reaction is nothing but total weight is shared by the two supports equally, W by 2. Then horizontal reaction also we know, WL square by 8H actually, but we are taking WL by 8H. So you will get its value. Maximum tension. Maximum tension T max. We know square root of VA square plus HA square. So VA is W by 2 square plus 5W by 4. This value will get horizontal thrust 5W by 4. Okay, because H by L is has given 10. So 10 by 8 means 5 by 4. So 5W by 4 whole square. So this value will get 1.35 W. So this value works out to be 1.35. W is 0.08008 A into L. Now maximum stress. He has given the maximum permissible stress. F max is nothing but maximum tensile stress by area of the cross section. So maximum tensile stress is, so A cancels out. So you will get 1.35 into 0.08008 into L. That's all. This is the maximum stress. Its value has given 150 newtons per mm square. How this value is given? So from this you will get length 1387.5 meters. Round it off to 1388 meters. Actually, this one is a 20 marks question in the mains, but he has given it 2 marks. Calculators are not permitted. Then such things you have to resign. If you attempt to solve this one, you will lose more marks, because assume that it has taken say 5 minutes time. Even further more time it will take it, because if you approximate also wrong result will come. Such questions we should not make an attempt. You must understand which questions you have to spend, which questions you have to guess, which questions you have to resign completely. Okay, 1388 means 10th question, C is the option. Finally, our aim is to get maximum number of marks. Not only one question we should solve and be happy with that. Spending 10 minutes means game is already over. Can we find it within 1 minute time or not? You have to see. If you cannot, means resign and go to the other problem. In the end, if at all you find time, you attempt it, otherwise leave it off. Those who solve more number of questions only will win the game. Okay. So how in the exam, how quickly you decide, shall we solve, shall I leave it? You have to first decide. Okay. 11th question. We solved it in the class same 1.4 second. This is solved in class. Next, 12th. Okay. Now numerical data. Maximum tension in the cable when 10 kilonewton load is moving from point P towards Q. So we have a hinge. This is the beam. There is a rope. Okay. He has given that it is a rope. Means it can only take tension, or cable. Whatever it is, both mean the same. This is 6 meters. Then this is 8 meters. Okay, Q, P, R. There is a load of 10 kilonewton is moving from one end to the other end. for what position of the load you will get maximum tension. If load is here, say, then here it is almost 0. But when the load is coming here, then it has to take more load because this will try to rotate. When the load is at P on the beam, then entire load is taken by the support itself. Tension in the cable is 0. As it is moving, it will try to rotate. And that rotational effect is maximum when the load is at Q. And that should be countered by the tension in the cable. So, you must keep the load at Q. The 10 kilonewton load should be kept at Q. Now here cut this cable. Then what this will do on this is tension T. 6, 8 means 3, 4. Tan inverse 3 by 4. This is standard result 36.87 degrees. Now he is asking what is the maximum tension in the cable. When it is here, T max. Maximum tension in cable occurs when 10 kilonewton load is at Q. Okay. Now take moments of all forces about P is equal to 0 because this you are cutting, throwing it out. T max you are replacing. So T max into sine theta anti-clockwise plus 10 into T max sine theta into 8 minus this is minus plus 10 into 8 must be 0. So T max is equal to 10 by sine theta. Sine theta how much? This is 3, 4 let us say. This is theta. Tan theta means 3 by 4. So sine theta means sine theta is 3 by 5. 0.6. So 10 by 0.6. 100 by 6. 16.67. 16.67 kilonewton. So like that. Next, 13th we solved in the class. Then he says, what is the cable? This problem we have solved it in the class. 14th solved in class. 15. A cable suspends across a gap of 250 meters. Across a gap of 250 meters. And carries a uniform UDL 10 kilonewtons per meter horizontally. This is 10 kilonewtons per meter horizontal. Calculate maximum tension. What is T max? To find this is VB, HB. This is T max. T maximum tension, if maximum sag is 1 by 25. It is not 1 by 25, it is L by 25. Maximum sag is equal to L by 25, not 1 by 25. So only this will become now 10 meters. Okay, this is solved in the class. Then what is the also compute sag at 50 meters from one end. This is 50. This is what is sag. So y is equal to 4h by L square into x into L minus x. 4 into h is 10 meters, L square 250 square into x is 50 meters, L minus x 250 minus 50. So you will get 4 into 10 into 50 into 200 by 250 into 250. Okay, so 50 into 5, 5 into 2, zeros cancels out. 160 by 25. 5 is done. 55 2s, 4 into 2, 8. 8 into 2, 160. So 0 cancelled out. 25 as it is we are keeping. Okay. Now this is, if we take 34 by 5. 6.8 meters. So sag here you will get 6.8 meters. It is not a linearly varying one, it is a parabolic one. Okay. So sag is 6.8 meters. Maximum tension I think we have calculated in the class 7911 kilonewton. H max 7812 kilonewton. VB 1250 kilonewton. Okay. Then extra is this one. What is the sag at? 50 meters from one end. Okay. Next. Now at this juncture, I must give you about the zero load testing I have given you.